Alright. So, did you guys get a chance to see what are the things that we're going to cover today? Let me read it for you guys. We're going to talk about vector addition, subtraction, and how do we apply parallelogram rules or parallelogram concept for doing that. Then we'll talk about vector addition and magnitude interpretation, meaning some more practical example of that. Then we'll talk about direction of vectors from components. By looking at the components, how do we find out the direction? And then vector components from magnitude and direction. So it's the reverse of what I mentioned just now. So direction of vector from the components and magnitude and direction to derive the components. These are relatable. And then we'll talk about some vector word problems. So today's class, if you guys have been able to follow me so far with respect to how do we deal with vectors, and if you are clear with the concepts, today's class is not going to bring a lot of learning. It is going to be a recap of what we already know. So let's get started. And I would want you guys to stay engaged, ask questions, participate to make it more fun. So if I'm talking about a vector A, which is like, let's say 5 units is the length and this is the direction. And if I'm talking about a vector B, which says, let's say 3 unit as a magnitude and this is the direction. If I say add vector A and B, are you guys clear how do we add the vectors? Do you recall? Okay, that's what I meant by staying engaged. So yeah, just to help you guys recall, if I'm talking about vector A and vector B, every vector has two parts to it. One is magnitude and one is direction. And so you can look at it that way. So this is the direction and this is the magnitude. Or you can always look at any vector A, breaking it down as the x component and the y component. And x and y component together gives you the magnitude as well as direction when you plot this or visualize this in a coordinate plane. So now when you talk about adding vector A and adding vector B, what you're essentially talking about is adding the x component of both the vectors and adding the y component of both the vectors. Okay? So if I'm talking about, let's say if this is my vector A and this is my vector B, this is my vector B. If I say A plus B, I'm not saying 5 plus 3. I'm not saying this. I never add the magnitudes together, or we are not supposed to add the magnitudes together, because magnitude of A and magnitude of B, it just gives you the exact value of or the size of the vector without taking the direction into account. But when you're talking about adding vector A and vector B, you'll essentially come to a point where vector A plus B will give you a third vector C, which will again have magnitude and direction both. Or if you say this is x1, y1 is my x and y component, and this is x2, y2 as my x and y component for B. So my vector C will have x1 plus x2 and y1 plus y2 as the x and y components, and obviously the direction. Is this part understandable? Okay. So in simple terms, if I'm talking about adding two vectors, I'm talking about adding the x and y components separately. Now let's visualize that in a more intuitive way. So if I'm talking about, let's say this is my vector A, okay, which has some magnitude and some direction. And if I have another vector B, okay, which has magnitude and this is direction. If I'm talking about adding these two, what I'm doing is I'm creating a chain. What I'm doing is I'm shifting this vector from here to here such that the tail of this vector gets attached to the head of the other vector. That is how it becomes A plus B. If this is my vector A and this is my vector B. What did I do? I moved vector B such that its tail or the origin point got attached to the terminal point or the head of the other vector. And what will be my resulting vector? This. This will be my C. So essentially, if you look at it carefully, and visualize this in a coordinate plane, what we are essentially doing is this. See, this was my vector A. This was the x and y. This was the origin point, some value, and from this one we got the delta x for A, the x component. And if you look at here to here, you got the y component, which is delta y. So when you look at A plus B, so here for this guy B, what is the x component? This is the x component. Or now I will relate it with this one. So this is a vector A. My x component is x1. So x1 is nothing but the difference between the origin and terminal point. Similarly for this guy, vector B, the difference between the origin and terminal point is x2. Now if you look at what happened to the third vector C, your x component you got added, x1 plus x2. So whenever we talk about, same thing you can compare in case of the y component also. Look at this one. What is the y component or the delta y? It's here to here. Here to here. This is delta y. So here y value is increasing. Now in case of B, what happened was the y value in this delta y is actually decreasing between origin and terminal. So this delta y becomes negative. So this positive minus this gives you the difference, this one. So basically this was your delta for this guy. This was the y component or y2 of this guy, and here to here was the y component of the first vector. This is negative and this one is positive. This is negative because origin to terminal is reducing, y value is reducing, and here it's increasing. This delta is positive, this delta y is negative for this second vector. So this gives you a difference. So eventually what's happening is your third resulting vector, if you relate, your x component got added, the y component also got added, only difference being this one had everything increasing, so it was positive, y was positive. In this case, the x value increased from here to here, but the y value decreased. So that's why this one became, let's say, if I am giving a number to it, let's say x component was 4 and y component was 5 for this one. This one was, let's say, 3, and this one was actually negative, let's say 2, because this is decreasing. I'm just making it up. So here, when you look at the x component, when you are adding this 4 plus 3, this became 7. That's what you see here, 4 plus 3 got added. But the y component which you see, 5 plus minus 2. So 5 minus 2. So this was 5. This came down to this place. This reduced by this. So 2. So 5 plus minus 2 gives you a 3. So this is 3. This is the reduced value. Am I making sense? I mean, are you guys able to relate? Dave, you have been quiet today. Am I sounding okay to you? Okay, I'm assuming Dave is probably struggling to figure out where the mute button is. But net from a concept standpoint, if you look at it, whatever I'm doing here, this is just to kind of derive some interpretation from this, which essentially means if I'm having two vectors to be added, I will not do the same exercise again and again. What I'll do is I'll take one vector, connect the other vector's tail to the head of the first vector, and then origin to end point, this becomes my resulting vector. So this was my vector A and this was my vector V. When I connected both of them with head and tail, head of one connected to the tail of the other one, this became my resulting vector, and the x and y component of that will be sum of x and y component of the two. Yes, Dave.
Wait, sorry, I issues and you were frozen for like 30 seconds. Can you repeat what you said?
Okay, so I'm saying it's a summary of what I said. Okay, if I have a vector A, this is A. If I'm saying a vector, that means it has an x component to it, it has a y component to it. Similarly, if I have another vector B, again this has x component to it and it has a y component to it. When I'm talking about adding these two vectors, I'm essentially moving this vector such that I'm not changing the direction, I'm just shifting it. Because we know that when you shift a vector, even if your origin moves, as long as you're not changing the direction, the magnitude, you're good. So what I will do is, I will just move this guy so that the tail of this vector connects to the head of this one, and this becomes my resulting vector. So mathematically, if you have to derive the resulting vector by doing A plus B, you have to do nothing, but there will be a vector C which will have x component as the x component of these two added, delta x plus delta x1, and the y component would be delta y plus delta y1. So that's what I was trying to show pictorially when you found me, frozen. But this is the takeaway. What I was trying to say was, we will never say this has a magnitude 5 and this has a magnitude 3. My A plus B will not give me 8. It will not be adding the magnitude. It's only adding the x and y components together. Because that is the most absolute way to break down a vector and then add them. Yeah?
Thank you, sir.
Now, if I have a vector B, if I have a vector A, which is this, can you tell me what will be minus A? What will be the negative of this vector? Visualize it this way. This is your coordinate plane. If you're saying A, you have a length. Here, between both of them, the magnitude is not changing. What is changing is the direction. It's a negative. Meaning, whatever is your x component becomes minus x. Whatever is your y component becomes minus y. Meaning, your origin, if your origin and terminal point were in this direction, your x was positive here and y was also positive. Now both are becoming negative. How will it happen? It just goes in the opposite direction. If you take a vector and flip it by 180 degree, that's a negative value of the vector. And if you want to really visualize this, look at this. This x component is positive. If you visualize this, your x component is negative. Your origin is some positive value and your destination is some negative value. X component became negative. So is the case with your y component also. Earlier it was increasing between origin and destination. Now it is decreasing between origin and destination or terminal point. So any negative of any vector is just going to be, if you look at it visually, if this is a vector, let's say k, negative k would be just the opposite of that. I mean, it need not start from the same point. You can always say, okay, fine, negative is same magnitude, same direction, but starting from different point. That is fine, because in case of vector, the origin point doesn't matter. As long as you are moving it in a more controlled way, without flipping the direction and without changing the magnitude, you are still fine. So, negative of vector is clear, right? Okay. Now comes the fun part of it, where you will. So there is something called parallelogram rule, and that is only to get you guys confused. People say, okay, I'll teach you parallelogram rule or parallelogram formula for a vector. That is crap. Don't have to worry about it. Okay. See, this is my vector A, and this is, let's say, my vector B. If I have to add them, we know it's simple. Add them meaning add the head and tail together. What I will do is, I will just shift this guy. and this becomes my resulting vector C. That's it. Or you will say, okay, fine, I don't want to add this way. A plus B will always be same as B plus A also, right? So whichever is first has head, tail and head. So first guy is head, second guy is tail. That is how you connect, right? If you, let's say if you're doing a tug of war and you're in the front, somebody who's holding you from the back, it's same way. This is the back of the guy. This is the front of the guy who is holding the rope. Let's say if you are holding him from the back or you being in the front, doesn't make a difference. I'm saying it's the same thing. A plus B is equal to B plus A. No difference. So same mathematical formula holds true. How will you think about it pictorially? If this is A and this is B, I can add the tail of this guy to this guy, or I will say this is my B, I want to add A to it. I shifted A from here to here. Now B's head is connected to A's tail. A's tail. Yeah? Both are same. Doesn't make a difference. And this will be a resulting vector. You start from the original one and go to the end one. That's your resulting vector. See. Now, what parallelogram rule says that you can add the vectors. Let's say this is your vector A, and I promise I will not delete them. This is vector B. Okay. Now, what are the ways you can add them to find out the resulting vector C? You will say, okay, this is my A and this is my B. This is one way to add the vectors. This is A and this is B. Now, or you will say, I will take B, I will do one thing. Instead of adding the tail of B with the head of this one, I'll say I will add B here. I'll put B here first, so that B's head connects to the A's tail. Now if you join this draws nothing but a parallelogram. So whether it's A plus B giving you C, or it's B plus A giving you C, both are same. See, there are two vectors you will get, either by adding adding A to the B, or adding B to A. Both gives you the same vector. This is C and this is C. So this is what the parallelogram says. Parallelogram rule says. I did it the other way around. Let's say this is your. I could have done it differently. Sorry, my bad. I did not put the right picture, and that will probably get confused. Let's say this is A and this is B. Okay. So I have two options. I can connect B to the head of A. This is A and this is B. This is B. What did I do? I connected B's tail with A's tail, and I connected B's tail with A's head. So it says, if you look at this is more like a parallelogram where you have A's head connected to B's tail, or B's head connected to A's tail, and this diagonal gives you the resulting resulting vector C. So that's what the parallelogram rule says. You don't really have to scratch your head to struggle with this. If you just look at this picture, this is your B and this is your A. Now you have two options. You take B as a base, connect A, or you take A as a base, connect B. Whatever be the case, this diagonal is your resulting vector always. And we already know A plus B gives you C. We are just visualizing this like a parallelogram. That's the only difference. And what this means is, be it A plus B or be it B plus A, both gives you the same vector, resulting vector C, which is nothing but the diagonal of this parallelogram that you can visualize. A connected to B, A's head connected to B's tail, or B's head connected to A's tail. Both gives you the same resulting vector C, which is the diagonal of the parallelogram that you can visualize here. Somewhat okay to believe? Yeah? Okay. Now, same parallelogram rule comes into existence for subtraction also. If I am talking about A plus B we saw. If we talk about A minus B, let's say this is my A, vector A, and this is my vector B. If I am talking about negative B, A minus B is nothing but, I can say A plus minus B. Okay? And now if I have B known here, what is minus B? Minus will be this one. This is minus B. So if I have to add A, if I have to subtract B from A or add A plus minus B, both are the same. So I will say okay, fine. Now this is a resulting vector. This became minus B and this is your A. This is a resulting vector. So don't think of subtraction being different. You are just talking about this and this being looked at with the same approach. That's all. This is your subtraction, this is your addition. You know that if I have a vector, negative of that is reverse of that by 180 degrees. And that is how you find out the subtraction thing. And same thing applies here. Here also you can visualize this as a parallelogram. So this is your, so you will say this, my drawing skills are a little scratchy. I know this doesn't look like a parallelogram, but I'm sure you guys will do a better job when you try drawing it. Yeah. So this becomes my B minus B here, and this remains my this one was A, right? So yeah, so this is, yeah, so this one is A. So both the case, this is the diagonal that of the parallelogram. It doesn't look like a parallelogram though, but yeah, got to trust me as a teacher whom we have been dealing with for some time now. Okay, so is this relatable so far? Anything that I'm getting you guys confused with, please feel free to remind me. Are you both clear about what I said so far? Now comes, so again, go back to the same basic. If we are talking about a vector, if I'm talking about, let's say, a vector A, essentially I'm talking about the magnitude and direction. Meaning this length is my magnitude, this absolute length, I will not care about positive or negative value. I'm saying absolute length, which you can relate with the distance formula also. In a coordinate plane, this is a starting point, this is an ending point, and use the distance formula to find out the length of this line. Now, when you have the absolute length, that is the magnitude, and this direction, and we learned that any vector that we have, we can break it down into two components, which is the x component and y component, which says the change along the x-axis and the change along the y-axis. So this is my y component and this is my x component, which says what's the difference between my terminal point and the origin point. What's the difference? Has x increased or decreased? Likewise, what is the difference between my y coordinates between the origin and the terminal point? Has it decreased or increased? That is my y component, and that's what helps us determine the direction. Correct? Now, if I have the magnitude given and the direction given, whenever you are given a direction, essentially that would say direction along the x-axis, along the point or the angle that this vector is making along the positive x-axis. So if you have the magnitude given to you and the angle that it makes with the x-axis, would you be able to find out the x and y component of this vector? Meaning, would you be able to find out this length and this length? It's a question. Applying basic Sukha, basic trigonometry concepts, whatever you call it. Yes or no? I'm not putting you guys on the spot. I'm just trying to get a sense whether if you have this information, let's say if somebody says this is 5 centimeter. This is the length, magnitude of this vector, and it makes angle theta. Can you find out the x component of this vector and the y component of this vector? Yeah. So again, nothing cryptic about it, nothing complicated. So I'm not going to spend a lot of time, but just for as a refresher, if I'm talking about magnitude and the direction, I'm talking about using this information to find out the y and x component. Now Sokatoa says that if this is angle theta, this divided by this, so delta y divided by delta x is nothing but your delta y by delta x is nothing but 10 of theta. Okay. So if you have the angle given to you, what am I doing? Okay. So let me not go that way. Let me do it a little differently. So here you're trying to find out the x and y component. So now let's look at it this way. This is your delta y divided by, let's say this length is 5 centimeter. Delta y by this will be sine of theta. If you know the angle, if you know this magnitude, so you can find out your y component of the vector would be this length, whatever it is, 5 multiplied by sine of theta, whatever angle is given to you. So from that you can derive the y component. Similarly, the x component will be this divided by this. So this is unknown, this is known, this is known. So you have only one unknown and two knowns. When you put that in the trigonometric function, delta x by 5 is your equal to cos of this angle. So cos of theta. So you can find out the x component as 5 times cos theta. And this 5 is just a number I gave here. What I was trying to come to was that if you have the magnitude and the angle given or the direction given, from that you can find out the x and y component. This is one of the things that we should be able to find out. Now let's say tomorrow somebody says, okay fine, angle, the direction given is, let's say 150 degree, meaning it makes 150 degree with the positive x-axis. So it probably goes up till here, 90 here plus 60 here. Okay, and then your magnitude is given, let's say, as 10 centimeter. Then you have to just visualize this such that this is 160 degree. So if you have to find out the x and y component, you can find out the absolute value and you can relate that with the fact that if it's 150 degree, you're talking about this getting to second quadrant, your x value will be negative. So you can find out the absolute value by applying the Sokatoa understanding and then look at which one is positive and which one is negative, and accordingly you can relate that with accordingly you can derive the x and y components. Is this part clear to you guys, or you would want me to double click on this one? I'm just going with the assumption that you guys know it already, but if I need to double click on that, I can do so.
It's clear.
Clear? Dave, is that clear to you, beta?
Yes, sir.
So there are 2-3 things that we are taking into account. If you're talking about finding out the component, right? Let's say if you're talking, you have to always visualize this with a unit circle understanding. If you're talking about a vector which is making 30 degree angle, then you know that you're talking about the first quadrant where x and y both are positive. If it talks about 120 degree, then you're talking about crossing this y-axis and making 30 degrees more. And then you have to apply understanding of trigonometry and then find out, this magnitude is known, this angle is known, you can find out the absolute value of the x and y component. This is your y component, this is your x component, and then visualize that in the coordinate plane that okay, my x is going to be negative or positive depending on which quadrant I am falling in, right? And then you substitute that value. So unit circle, trigonometry, these two things if you put together, you'll be able to find out the x and y component. But the underlying concept will remain the same, no matter what the angle is. Your x and y component is nothing but, whether it's facing this way or this way, your x and y component will help you determine the direction and the magnitude, or the vice versa. The magnitude and direction will help you determine the x and y component. Yeah? Now, let's look at what extra I had put in here as a plan. So we talked about vector addition, magnitude, interpretation. Okay. Vector addition, magnitude, interpretation. Yeah. We'll double click on that aspect a little bit. Direction of vector from components. So if you have, okay. So direction of vector from the component is what we have not touched upon. And the vector addition and magnitude interpretation. These two things we have not covered. Vector components from magnitude and direction we talked about. How do we break it down? Okay. So we'll talk about direction of vectors from the components. Okay. So let's look at it. Let's take a practical scenario. Okay. If I say I have a vector k. Now there is nobody with a k here, right? So let's say I have a vector p, that is for pressure. Okay. And I have a vector d, that is for Dave. Vector p has x component as -2, okay, and vector d has x component as 2 and 4. I am purposefully taking same value with one being negative. Now from this one, can I find out the magnitude and direction? I have x and y component. Obviously, if you have to find out the magnitude, we know that magnitude is x squared plus y squared, square root. So I'll say okay fine, what is the magnitude? It will be -2 squared plus -2 squared plus this one 4 squared, the square root of this. That will be my magnitude of pressure. And this is how we represent this. So this will be nothing but 4 plus 16. The square root of 20 is my magnitude. Same thing for vector Dave. Also I got my magnitude as 2 squared plus 4 squared. Same value, 4 plus 16, the square root of 20. I got the same magnitude because the numerical values were matching. Now, what is the difference here? When I look at x component as -2, what this essentially means to me that the vector pressure x component is decreasing. Meaning, if this is my coordinate plane, if I want to visualize 2 points, for pressure, this is decreasing, meaning this is something like this. I mean, if I just look at the x part of it, x originally was more, it became less, and y component is increasing, meaning y value is increasing. So this is what looks like to be the vector pressure, because the x value is decreasing and y value is increasing. Now, if you say from this calculation you found the magnitude, you know the length of this vector, but what is the direction? You are able to find out that this is this way, meaning you have to find out this angle, or let's look at it this way, or look at this is called, we'll find out this angle and then subtract that from 180. that will give me this angle's value or the direction. So let's look at it. We know that this is x is minus 2, which we can see, right? If this was my origin, this is minus 2, correct? And this is 4. So what is this angle? This is this by this minus 2, or this will be this by this gives me tan theta. So let's say this is theta. So tan of theta is 4 divided by minus 2, which is minus 2. Now I will find out this angle as tan inverse, which your calculator will help you find out. Tan inverse of minus 2, that gives me this angle, and I subtract that angle from 180, that gives me the direction of this vector, and magnitude we already found out. So if you have the components, you can always find out the direction, as we saw just now. Was it simple enough to follow, or as always I am able to confuse you guys? So you guys are agreeing to the point that I am confusing you always as a teacher, no? Bad news. Okay. So this is, see, we saw this one. Okay, sometimes you have to bear with my bad jokes, okay? Now, the second one is, this was the negative scenario, when we saw minus 2 and 4, minus 2 and 4. Now look at the positive scenario. If I am talking about second vector Dev, this is 2, 4, meaning my x value is positive, my y value is also positive, meaning between origin and terminal point, my x value is increased by 2 units, and between origin and destination point, my y value is also increased by 4 units. So this seems to be the vector Dev, where origin and terminal point is increased by 2 units, and origin and terminal point increased by 4 units. Now here I have to just find out this angle, which will be fairly straightforward. It will be, here it was tan inverse of minus 2, it will be, here if you see tan theta equal to 4 by 2, which is 2. So in this case, theta will be equal to tan inverse of 2. And from that we can find out this angle. And this time we don't have to do any magical calculation, because here it was a derived theta value and we had to subtract that from 180 to get this angle. Here it is making the angle with the positive x-axis, so should be fine. Is it making sense? I mean, are you guys able to see the difference between the difference in the direction based on how your x and y components are changing? At least with the sign. No comments? I mean, is this relatable? If it's not, I'll come back to this again. Okay. So the summary of this is, if we know the components, we can find out the magnitude and direction. Or if we know the magnitude and direction, we can find out the components. And it all revolves around our understanding of unit circle, the coordinate plane, and the basic trigonometric functions, or SOHCAHTOA, whatever you call it. Yeah. Now there's an interesting. I'm kind of tired of teaching now. Let's engage into interesting discussion. If I give you guys a scenario that if I have vector A and I have vector V, okay, so magnitude of vector A will be this, magnitude of vector B will be this. Now a question to you guys is, will the magnitude of vector A plus magnitude of vector B will be equal to magnitude of vector C, which is same as this, or will it be greater than equal to this, or will it be less than equal to this? So let me not confuse you guys. Will it be greater than this? Will it be less than this? And will it be equal to this? Or let me simplify this for you guys. Let's say magnitude of vector A is 4, magnitude of vector B is 3. If I add vector A and B, so if this was A, this was B, I added them, I got a vector C. So I'm trying to find out, will the magnitude of vector C, which is sum of A plus B, be greater than this, sum of these two, or will it be less than these two, or will it be equal to these two? Thoughts? So before I force you guys to give me an answer, did you guys understand the question in the first place?
Did you say the question again?
Yeah, I have two vectors A and B, as you can pictorially see it also. Okay? If I add vector A and vector B to get a resulting vector C, and by now we all know how to add vectors, right? So if I add vector A and B and get a vector C, I'm trying to understand what will happen to the magnitude of the resulting vector. Will the magnitude of the resulting vector, let me put it as a C here so that you guys don't worry. C is nothing but same, A plus B. Will the magnitude of C be less than sum of these two, greater than these two, or equal to these two? Is the question clear now? Dave, how about you? You guys take a minute to think about it. I'll just grab my water bottle. Okay. Do I have the answer? And again, there's no wrong answer, okay? I'm still just trying to pick your brain to see how do you relate it.
Would it be the magnitude of A and B is greater than?
I would not know whether the answer is right or not, but tell me what is your thought process? Why do you feel so?
Because, like, in a right triangle, the hypotenuse is like less than the sum of the two, right?
Mm-hmm.
So,
But is it?
like, using the same theory.
You are thinking in the right direction, beta, okay? I'm just trying to refine that. Now tell me one thing, did I say that this is going to be right triangle? Two vectors will never be right triangle. And I mean, it never guarantees that there will be right triangles, right? I mean, I can have a vector like this, and I can have another vector like this.
Right.
It might not turn out to be right triangle, right?
Yeah.
But you are 90% correct, and you are thinking in the right direction. Now there is one thing that you would have learned at a very early age, before you even heard about me. That is, any triangle you pick up, sum of the two sides will always be greater than the third side, no matter which one you are picking. Sum of the two sides will always be greater than the third side. And if you want me to prove that, look at this. If I have one triangle, okay, this is one side and this is second side. If I add this and this, it will be always greater than this. If I pick this side and this side, if I sum them up, it will be greater than this. If I pick this side and this side, sum it up, it will be greater than this. And that has to be the thumb rule. Otherwise, you will not be able to draw a triangle. If you ever try drawing a triangle with 3 lines where sum of these 2 sides is not greater than the third side, you will not be able to draw a triangle. Look at it. If these 2 are not greater than this, if these 2 are same, that means you will not be able to make an angle. This will literally fall on this. Yeah? These sides have to be bigger. That is how this will not collide with this baseline, correct? And the same combination you can think of. So, thumb rule is, in any triangle, sum of 2 sides has to be greater than the third side. No matter which one you are treating as A, which one you are treating as B, which one you are treating as C. Any 2 sides, some of the 2 sides have to be greater than the third side. So will be the case here. Now when you are basically adding two vectors, you are talking about essentially 2 sides. And that magnitude of the 2 sides, that has to be greater than the third side by default. So here in this case, you will say this is one scenario, and now look at 2 vectors. See, if I have 2 vectors, they can coincide on a line also, right? I can have 2 vectors, the same direction, different magnitude. When I add them, I end up drawing a straight line. Am I making sense here? Yeah, and trust me, you don't have to be compliant for saying yes. Okay, if there's tiniest of the doubt, you have all reasons to ask me and stop me. Okay, so here I'm saying I can have a second scenario when my 2 vectors have the same direction but different magnitudes. And if none of them, see, if I have 2 vectors with the same magnitude and same direction, they are not different, they are same. But if either the 2 parameters of a vector, be it magnitude, be it direction, if they are differing or if both are differing, that is how they are different. So here magnitude is different even if the direction is same. So what will be the sum of A plus B will nothing be but will end up joining the 2 lines. It will become a straight line. So this is a second scenario where there could be a possibility if A and B have the same direction, then it can be equal to C. The magnitude of C could be sum of these 2, as you can visually see. Yeah. So, the interpretation from this is that if you have 2 vectors and if you add them together, the magnitude of the resulting vector has to be either less than the sum of the 2 or at best it can be equal to that. Does it sound like an interesting correlation to you guys? Yeah? Now, I had also mentioned one topic which is called word problems, and I will not even talk about that. The reason being, word problems are coming from nowhere. They are all about the concept that you know. See, whatever we have done, the word problem would be an extension of all the things that we have learned, and they will be relating to all these concepts. If I have vector A, what will be negative A? Same thing. This is negative A. The action flips. If I have vector A and I have to add another vector B, I will connect the tail of this guy and the head of this guy, and that becomes my output or resulting vector. Or I will connect the head of this guy with the tail of this guy by moving it here. Right? What did I do? So I can connect it, the tail goes here, or I will say I will connect the tail of this guy here, and this becomes my resulting vector. So basically, we know how to add it. If you have to subtract, it's as good as adding one with the negative of the other one, and we know what negative means. And that is what the parallelogram rule also we saw. Now we also saw the fact that if I have 2 vectors, some of the 2 vectors the magnitude of the resulting vector will be less than the sum of the other two vectors, or at best it could be equal to that. Now when you talk about word problem, it'll relate to these concepts and you should be able to solve it very easily. I mean, I saw myself a couple of word problems. They were all just blabbering, in a paragraph, and when you read it carefully, apply this boarding concept, read it a couple of times, note it down, do your analysis, you'll be able to do it. So that's why I'm not going to the word problems. I did not find any very qualifying or meritorious word problem to solve. As long as you know the concepts, you'll be able to apply that. So my only request to you guys would be, this brings us to the end of the unit 6 in Khan Academy. My request to you guys would be, at least go to the last unit test for vectors and try solving it without even bothering to see what we have covered, what we have not. And all the concepts that we have learned, if that is learned well enough, you should be able to solve. If you are getting stuck anywhere, catch hold of me here. Okay? Alright? And whoever wants to catch hold of me with my collar has to be in DFW, okay? So Prisha has that option. Dave has to book a flight ticket for Dallas. Alright? So with that being said, I will let you guys go. Enjoy the rest of your evening. I know you guys are having your Christmas, not Christmas, spring break, at least for kids in the DFW area. For Chicago, I think you guys have 1 more week to go. Alright, have fun. See you guys next week or on weekends.
Thank you, sir.
Alright, bye bye.
Thank you, sir.
Bye then, bye bye.